Tonight we are delighted to have as our speaker Alberto Conti, an astrophysicist and NASA multi-mission archive scientist at the Space Telescope Science Institute. The Hubble Space Telescope has led the way in a revolution in astronomical imaging surveys, but the sheer volume of data and how to make it available remain challenges for the astronomical community. GoogleSky is an attempt to develop an intuitive visual interface to make the Hubble data easily available to anyone at any time, at any place. And tonight we will hear about that project. Dr. Conti received his PhD from Ohio State University and did postgraduate work at the University of Pittsburgh before joining the Space Telescope Science Institute. He is the author of numerous publications, in particular on the analysis of large astronomical data sets. Please join me in welcoming Alberto Conti.
Can everybody hear me? Well, I have a loud voice, but I want to make sure everybody can hear me. Well, thank you very much. Thank you for the Society for inviting me. It's a true pleasure being here. I'm going to take you over the next hour, I hope, in a journey. Before I do so, I have to give you some information about what I do, who I am, and why this is important, at least to me. So as was mentioned, I work for the Space Telescope Science Institute, which is the institute that is the Science Operations Center for the Hubble Space Telescope. And it will be the Operations Center for its successor, the James Webb Space Telescope, which is scheduled to launch at the end of this decade. Thanks. I am at the Space Telescope Science Institute, the archive scientist. So I work for what's called the Multi-Mission Archive Space Telescope, whose acronym is MAST. And MAST is the optical and ultraviolet data archive for NASA. It was established in 1997, and basically has the mission of collecting anything that is space-based, coming from ultraviolet and optical satellites. Hubble is obviously an optical satellite, but there are other missions, such as the Galaxy mission, which is an ultraviolet satellite, so it looks at the universe in ultraviolet light, and I'll show you what that means in a few minutes. And then we have active missions, so Hubble is still active. It will be active for the next foreseeable future. Kepler is a mission that is actually out to find planets that are similar to our own, to do a census, if you will, of planets. And we collect the data, we distribute the data to the astronomical community. MAST, so the optical archive, is not the only archive, obviously, that NASA supports that does collect imagery and the data from astronomical missions. And it's part of a series of archives. And in particular, these are perhaps the three best known, at least in the astronomical community, but I wanted to give you a census of an idea, at least, of what kind of data we also store. We store data from Hubble, but we do store a lot of data from many other missions. Vital to astronomy is publications. So the Astrophysics Data Systems, it's called ADS, collects all the publications that are made in astronomy since 1640, I believe. And then you can basically collect a record of who we are. So this is basically the publication archive, if you will. If you're interested in X-rays and high-energy physics and high-energy events in astronomy, then you go to Goddard Space Flight Center, actually, which is where the HESARC, the High-Energy Astrophysics Science Archive, resides. So it's X-rays and gamma rays, high-energy astrophysics. And if you're interested in infrared science, you go to the West Coast, where you have the infrared science archive, URSA, and the extragalactic database known as ED. So these are the archives that NASA supports and funds. MAST has a very simple mission. Basically, we have 4 points that we want to get across the astronomical community, and one is we want to be the leader in technological and scientific achievements, if you will, in archiving data and being able to deliver data to the astronomical community. We have to achieve the first goal, we have actually to provide secure and reliable storage for all the data, and I'll show you how much it is and how interested the community is in this data. And then we have to do this in a user-friendly manner, and I'll show you why that is I would actually say not only important but a must to do, is because scientific data comes in very different ways, and we have to have a way to sort of showcase the data to the community, but not only astronomers, but also to the public, in a way that is compelling and actually drives the curiosity, if you will, of astronomers and science in general. And then we have to also do something which is, we have to be good citizens and actually take a look at other archives and what they do, and try to collaborate with them effectively. So what I wanted to do tonight is take you on a journey. And the journey will basically take us through space and time, and we'll start at Earth, a place that we kind of know. And then we'll move on to our solar system. We're going to explore near planets. We're going to explore planets that are even further out. And then in this trip that I'm going to take with this tool that I'm going to show you, we're going to move even further away. We're going to go and take a look at stars that are dying. We're going to look at stars that are at the end of their lifetime and die in very different ways, even though the mechanism of death is the same. We're going to take a look at how Hubble sees these stars dying. And we're going to go even further away and take a look at things that are really incredible, but yet are things that we understand are stars at the end of their lifetime, pretty much like our own sun. We're going to take this is, we'll call it our solar neighborhood. We're going to move further away, and we're going to look at galaxies that are similar to our own, that contain 200, 300 billion stars like our sun. We're going to go even further away and look at environments where galaxies are seen through the eyes of Hubble, smashing into each other and merging to form new galaxies and new stars. And we're going to look at things that are really strange, that we think are stars, but in reality are billions of stars. So this is a galaxy that has actually gone to another galaxy. We're going to look at even larger scales and go even further away in the universe and look at clusters of galaxies where the gravity is so strong that it can bend basically the light from galaxies that are behind the cluster. And ultimately, we're going to basically take a look at things that are so pervasive that can bend light everywhere, and that's called dark matter. And in all of this journey that I hope I'm going to take you, I'm going to show you tonight, is the fact that there's one goal that we have, regardless of what kind of data you're looking at. And the goal is to try to understand the footprint, if you will, of our universe. How does it look like? What does it behave like it does? And how can we, sort of browse this incredible collection of images and catalogs and data and information about objects in the sky. Except we have a few problems. And space is big, I'm sure you know. Space is very big, and if I had an average camera, like you have in your pocket, with not pretty good resolution, I would need 2 trillion pixels to take one image of the whole sky. And so 2 trillion pixels, just to put it in perspective, is about 4 terabytes, which these days is actually not very large. It's about 6% of the Library of Congress as of a year ago, perhaps. So this is a manageable size, which is comfortable. Except astronomers want to do more than just take one picture, obviously. We want to take several pictures because we want to make all the color images that I showed you before. And so we need hundreds of terabytes. And that's, let's say, 40% of the Library of Congress. But astronomers also want more. And what is more? Well, we want to take a look at the objects that change in the universe. We want to take a look at things that are going boom, perhaps, that are exploding, things that are changing in luminosity, galaxies that are smashing together, things that are changing. And if we want to do this, the amount of data that we have to look through, that we have to sit through, is actually of the order of tens or hundreds of petabytes. And that becomes a little problematic when you want an answer before your lifetime. So what we have to do is take a look at the problem, try to break the problem in simpler steps, and try to figure out what we could do to introduce new analysis and visualization techniques so that we could analyze 10 or hundreds of petabytes in a reasonable time and get answers that we want. I have to say that to be objective and say that this problem of having massive amounts of information is not unique to astronomy, quite the opposite. Computer science has shown us in the last 40 years that this is a very, very big problem. This is a very common problem, and they have indeed provided incredible solutions on how to do this. But biology, these days, and I was talking actually at dinner tonight, biology and medicine are actually exploding in terms of the amount of data we can collect. And so once you have to collect this data, once you've collected the data, you need to be able to analyze the data again before your research time is over on this planet. The government, which is something that perhaps people don't think about as generating massive amounts of information, is actually generating tremendous amounts of information. So astronomy is really no different. And the bottom line is that all of us are really crumbling under data. We're really being hammered by the amount of data that is being given to us to understand a universe, in my case. And we have to try to make sense of this data. So astronomy has been changing over the past 30 years. And we have been able to grow, if you will, to build telescopes about 30 times the size that we used to be able to build only 25 years ago. That's pretty impressive. But what's more impressive, that we've done 100 times better when it comes to detectors, when it comes to chips that can actually image the universe. So we had 3,000 times the number of pixels that we used to have only 25 years ago. And since the detectors and the pixels follow a law, an empirical law that tells us that they double every 18 months or so, it turns out that our data, the whole data, is doubled every year. And this is, again, it's a problem. And we have to try to address this problem. Compounded to this problem is that the more data we give to the users, the more they want. So at the bottom here, you see, for the Hubble Space Telescope, you see how much data we deliver to the community as a function of time, since 1995 to basically last year. We deliver about 15 terabytes per year. However, the amount of information that people, the amount of data that people come to get at the archive is about 6 times that number. And what is really remarkable is that in this timeline, if you will, in this green line that shows us how much data people really want to get out of the archive, because it's very important data, because it's very interesting, as I will show you next, we can actually identify places where some instruments weren't working, for example. So the Hubble Space Telescope was serviced a few times. The third servicing mission had installed 2 new instruments, the Advanced Camera for Survey and NICMOS, and you can see a big bump in our data holdings, and also it's kind of hard hidden here, but also a big bump in a few months afterwards on how much data people were interested in. And then at some point, the Advanced Camera for Survey dies, and then so we don't ingest information anymore into the archive, but still people are quite interested in getting the data, the previous data that we have ingested over the last few years. And then the last servicing mission in 2008 not only fixes two instruments, but puts 2 new ones. So we have a huge jump. And so our trend is actually quite astonishing here, but this is 6 or 7 or 10 times more data that users are requesting. So we have a lot of data, we have to learn how to deal with this. But I think, at least for astronomy, I see hope in my life, in the sense that I think we're a little special. I'm biased, but I think I'm trying to be objective, and I think we're special for a few reasons. Astronomical data is completely worthless. There's no commercial value. At least I haven't found one. If someone has a bright idea, please let me know. We can fund the research. But basically, there's no commercial value. And it's ideal test bed because it's large, complex, and poses interesting problems. It's an ideal test bed to test complex mathematical, statistical, computer science algorithms. And as I tried to tell you in the last slides, there's plenty of it. So some of us, in the last few years, have looked at the fact that these 4 bullets seems to be true, and try to engage other communities to try to help us to solve some of our problems with our data. And it was really we only had one option. We had to adapt or we had to perish, and we chose to adapt. So if we take a look at what has happened in the geographic information system, so on Earth science, if you take a look at Google Earth and Microsoft Picture Earth, they've kind of revolutionized, at least for me, the way I look at the planet, the way we are able to browse the planet. And I will show you that as my talk goes on. It's truly remarkable what we have been able to do and how we've been able to look at our planet. And so what we decided to do was, to some extent, images are images. Is it true that we can adapt something that is seamless and easy to use, and for which there's no manual, and that serves, if you will, the Earth on a silver platter for any user to browse sky images? Mostly, what we wanted to do is inspire people. NASA's been inspiring people for many, many years. I think Hubble has inspired people for the last 21 years into orbit. But in reality, my generation, perhaps even people that are younger than me, have been inspired by taking a look at our planet from just our moon. And so this inspiration is something that drives, I guess, many of us, and is what sort of drove us to try to attack the problem and asking other communities to go from here to here. We wanted to basically give put the universe, so to speak, at your fingertips. And we did that.
Flying around the globe with the click of a mouse. That's what Google Earth users have been doing for years. But now the folks at Google and the Space Telescope Science Institute have teamed up to give you not just the world, but the universe.
I think we felt that there was a gigantic void in terms of how generally the public perceive space. Sky Google Earth is an application that allows anyone really to browse sky data like you are allowed to do when you have Earth data.
Using imagery from observatories on Earth, as well as stunning photographs taken by the Hubble Space Telescope, everyone from astronomers to curiosity seekers can now get a closer look at worlds seen from the eyes of Hubble.
In particular places of the sky, there's just this exquisite resolution. So it's like having, a brand new camera with just amazing resolution.
Learning to navigate the sky will be no more difficult than the way you already globetrot with your computer. Future upgrades to Sky and Google Earth may even let amateur astronomers add their own images.
Space is already a wow factor in itself, because when you see these beautiful images from Hubble, but then we're going to give you a different perspective. There's no way to really browse this gigantic amount of data that is available out there on the internet other than still pictures.
Zoom in and out of your desktop universe and you'll see high-resolution Hubble images, along with the names of some of their celestial neighbors. And if you're interested in learning about a particular object in the sky, type in its name and Google takes you there.
Our goal at the beginning was, let's take this client and have it on every kid's desktop.
It's just easy. You don't need an instruction booklet. You don't need to take a course. You just load up the software and away you go.
On a journey to galaxies that we know about and those that have yet to be discovered. From the Space Telescope Science Institute in Baltimore, Maryland, I'm Mary Estacion.
So this was our press release on August 22nd, 2007, after working with Google for about a year and a half. And in this press release, you saw two of my conspirators, I guess. Carol Christian, who is also an astronomer, with whom I worked for the length of this project, and also my student who contributed to many of the things you're going to see tonight, which is in this room, is Josh right there, who actually was the guy who had the idea of doing this video. So thank you, Josh. So let's start a tour. Let's show you what we actually did. Before we actually do something, I have to show you what Google Earth looks like. So I always start from the center of the world, which you might view as Italy. So we start in Italy, and we have a canvas. The way I think of this is a canvas. And on this canvas, we can draw stuff, right? We can draw things. We can draw, let's see what we're going to draw. We're going to draw clouds. We're going to draw rain. That was a few days ago when I did this video. And then we can draw temperatures, and we can actually decorate, if you will, this canvas. The breakthrough was the following, that as I travel now from Italy to the Space Telescope Science Institute in Baltimore, not only we're going to go through the clouds, because the clouds have been placed at the proper altitude, and the rain as well, but I'm going to give you only the image detail that you need to go from Italy to Baltimore. And I'm not going to bother to give you details that you don't see, because it's irrelevant. This was a big breakthrough. I can give you very little information compared to the whole size of the data set, if you will. So these are tens of terabytes that I don't have to stream to your Mac, in this case, to your computer, to your iPad, and whatever it is. So this is the Space Telescope Science Institute where I work, and when this image was taken, actually, that one is my car. So this is a detail. I can go from Italy, from looking at things in space, from space of tens of thousands of kilometers up, to something like this. And not only I can draw, but I can tilt in this. I remember it was raining the other day, so there's rain here too. I'm going to remove the rain in a second because it was bothered by the rain when I was doing this. But I like the earth and the sun. But the idea was that not only you can actually draw in 3 dimensions because we are on a sphere, if you will. We can actually draw things on this canvas. What are we going to draw? Well, we drew the, Google has mapped almost the entire world, but this is the campus of the Johns Hopkins University. And it's interesting because of the things I'm going to show you in the future. But the idea is that the ease of which you can browse the Earth and the ease of which you can see details when you need them. I am very far away now from the Space Telescope Science Institute. I'm going to actually to where we are tonight. And I don't need to see the details of my car at this altitude. And therefore, I'm not going to give the machine, if you will, the information that it needs to show me the car because it would be irrelevant. I would not be able to see it. And then this process, which was invented actually by Microsoft about 5 years before Google, but Google sort of reinvented or rediscovered it and implemented it in a different way, allows us to browse and go from place to place and to sort of decorate a sphere in Earth. I'm going to call it a sphere because you'll see what I'll do next. So this is where we are tonight, and you see all these grayish buildings. I apologize for the choppiness, but it's a little video. But these gray buildings are actually the buildings here where we are, and they've not been sort of colorized like some of them have been, like some of them in the corner have been. But we're not actually here, we're here, but that's close enough. And the other thing we can do, we can actually decorate this canvas with other information. You can actually say, okay, I'm here now, what is the Cosmo Club? And so we can actually have information about what the Cosmo Club is.
Wow.
So this was simple, and it was done by Google for Earth. And when we saw this, I guess Josh and I and Carol, we realized that there's a lot of power into this interface. So the first thing I did was like, okay, I like the Earth, but I like space better, so where's Hubble? So Josh and I work on this code. We put the actual orbit of the Hubble Space Telescope at a proper altitude in real time for everybody to browse. So we posted this on Google servers, and you can go get it now. You can see what Hubble is. It actually moved when I was playing with this. And the interesting thing is that we did this, and Josh actually worked on all of this and actually gave information about Hubble, where it is, what instruments are, and so on. The other thing is, once you have one satellite, you should ask, where are the others? I mean, why not? And so we did that. So we asked, where are the other satellites? And you realize, wow, there are a lot of satellites out there. And I'm going to scare you in a second because there's actually more debris than satellites. So the debris are going to appear in a second in red. And that's what scared us a little, because you can actually plot all the debris as well. So this is actually debris where, so if you didn't think we had a problem with debris, well, we might have a problem very soon. So the idea is, again, this is a canvas. This is a three-dimensional canvas. I have a camera, I can move around, I can browse imagery. I don't need to see the detail of where we are right now because I'm so far away from Earth, 27,000 kilometers up. But I can decorate this canvas if you do that. So what if I substitute this canvas for something else? Well, let's do it. Let's go to the moon. And by the way, I'm going to put here the time from Earth. We're 1.3 light seconds from Earth. So if you follow this, you know how far you are from Earth. So if we have a sphere, similar to the moon, we can actually do exactly the same game. More resolution as you zoom in, more detail as you zoom in. And this is the landing site for the Apollo 11. And you see all these strange images and pictures and everything that Google has added. But this, for example, we can draw buildings on Earth, so we should be able to draw three-dimensional modules on the surface of the moon. And which is something similar. I haven't shown that to you on Earth, but we can do something even more remarkable. We can actually ask, what was Buzz Aldrin looking at when he took this picture? So we can actually immerse ourselves in what Buzz Aldrin was looking at through this sort of artifact, if you will. We can actually project at the correct distance and on the moon, on the same place where he was taken, a photo of the Buzz Aldrin took of the lunar module. To me, this is pretty remarkable because there's a lot of information that has been served, if you will, to your eyes that it's, and the way it's being served is actually pretty impressive. Let's keep going. What's up to the moon? Well, I want to go to Mars. So let's go to Mars. We're 8.3 light minutes away. From Mars, we're going to go to a strange place. There's two rovers, actually one now, because one is dead. There are two rovers on the surface of Mars. We can actually zoom in on Mars. And you see this is actually not very high resolution. But on Mars, we can actually build three-dimensional models like we do on Earth, or like we do on the Moon. So this is one of the 2 rovers, Ability's Opportunity, that's still working. And it was here a long time ago. However, Mars there's an orbiter around Mars that takes very high resolution images. And so we can ask, okay, can we figure out where the rover went? And lo and behold, here's the tracks, the red tracks you see are where the rover went. And we can even play the same game we played with Buzz Aldrin on the Moon and ask ourselves, what are we looking at? First of all, because we don't know, so we can ask, and we're going to look at the panorama from Cape Verde, which is this crater that Opportunity surveyed. And we can actually immerse ourselves in what the rover looked at, really, the picture that the rover took. And take a look at very close pictures and images of rocks. Maybe boring, but rocks on the surface of another planet. This is pretty impressive. This technology is very impressive. At least it is to me, and it was to me when we wrote the proposal to Google to actually extend this to things that are not Earth-based. But let's move a little further away. We can take Jupiter. And instead of actually modeling three-dimensional Jupiter, which is a little boring because it's a pretty flat and gassy planet, what we do is we actually say, Hubble has observed this planet a few times. Can we animate? Can we actually show how the surface of the planet shows what's called differential rotation, where some layers rotate at different speeds, and a strange effect around, for example, this big hurricane that's been going on for hundreds and hundreds of years, for instance, Galileo's. So one of the aspects of this Google software of Google Earth every day, and now Google Sky, is the fact that you can actually tag time in this particular environment. And we are only 50 minutes away. The other thing you can do is that you can draw a dimension, you can draw satellites, why not draw rings around Saturn? And what I did, I thought was actually kind of cool, is, and interesting to me, is you can simulate what the Cassini mission would do when he flies close to Saturn. You can simulate a little flyby of the Saturn rings, and it just for probably no scientific purpose, but I thought it was nice. It's interesting what you can do by looking at, by using exactly the same interface and exactly the same code that you use on Earth to draw buildings, if you will. Then we can look at even further away. How many of you knew that there's another planet of the solar system that has rings? This is images of the Hubble Space Telescope of the planet Uranus, taken at 3 different years. And you can actually clearly see that some poor moon experienced a little stress and were actually shred to pieces by the gravity of Uranus. And then as Uranus revolves around the sun, its inclination changes. So in some inclination, you hardly see the rings, but in some other inclination, you actually do see the rings. And this is remarkable. This is something that only Hubble can do in space. About 3 hours from the sun. You can also take images from Hubble and just say, okay, well, we know there are moons on Neptune. What are their orbits? Can we follow them and trace their orbits? Well, Hubble has done a few things like these, and so we can actually trace the orbits of some of the moons around Neptune. And in this way, one can imagine if we have a resolution, we might find things that we didn't know existed before. Pluto, which was a lot in the press lately because it was demoted to a dwarf planet, turns out actually that Hubble discovered a few years ago that Pluto actually has 2 moons. This is Charon, this is a Pluto-Charon system. We knew they existed, were observing life in the early 1900s. And then these are 2 moons that were discovered by Hubble by observing them. So I'm trying to show you, this is not Google Earth, but this is what kind of resolution you see Hubble provide to astronomers. And you'll see why I'm focusing on this, because you're going to see what I consider tremendous images showcased by Hubble of our universe in GoogleSky shortly. So before we leave the solar system, let's take a look at our sun and all our planets, and we're going to rank them by...
It's 9 o'clock.
Thank you. And that's my machine. And it's... I need to know what time it is. And these are the planets, and then this is our little planet. And I put this here because it gives us an idea of the scale, but also gives us an idea that we, as a species, have launched something which is 16.5 light hours away, way out there in the solar system. Not very far, because as you will take a look at this number will go into the billions very quickly. But it's something that we have done. And I think it's interesting that our species has done this. But we have, think about this, we have conquered just 16.5 light hours away from our sun. We are really in our infancy. And it does take some time to take a Voyager 1 to large distances like this. So I think, if I'm not mistaken, this was launched in 1977. Okay, so let's turn our interest now to the closest star to our own. So we are on Earth here. Well, I'm tired of looking down. We're going to look up. And so we're going to enter GoogleSky. So I'm going to describe this for a while. But the idea is that we can do exactly, we can have the same process. We can take you to take a look at what was imaged from the ground, a star which is kind of similar to our own. It's 4.2 light years away. And this very little faint star right here at the center, in very, very coarse resolution. We'll see much better resolution very soon. This is our closest star. And the idea is that we have the same mechanism again that we had on Earth, on the Moon, and on Mars. We have basically zoom in around the universe in this case, so to close stars, or to, as you see, galaxies in a few minutes, and we can decorate this canvas, if you will, now with constellations, because that's what's important for, let's say, the public to see. And here you see Gemini. It's actually, incidentally, a very nice constellation that were drawn by hand in the early 1200s, if I'm not mistaken. And we actually took them, we put them actually in this sort of environment, if you will. You can also have the boundaries of the constellation themselves, for example, to give you sort of a reference frames. And you'll see all these dots here that appear. And as with cities and populated places on Earth, these dots represent what's important, what's relevant at this particular resolution. So you're going to see stars, all these white things. You're going to see things that are galaxies, and you're going to see much more. You're going to see what Hubble can do with this data. So let's show you first 440 light years away, the Pleiades, which is a group of stars, very, very young, maybe 1 million years old, very, very. I forgot to mention this. I apologize. So as you did on Earth, when you click on the cosmocloud, you can actually click on a star to actually have information about a particular star, its location, its temperature, for example. And you can do this with any of these objects. And as you see, these objects are appearing as we zoom in, like my car appeared when I really, really zoomed in at the Space Telescope Science Institute. So as I said, we look at the Pleiades, a group of stars maybe 1 million years old, very, very bright. This is not a Hubble image. This is an image taken from the ground. And this fuzziness is because the atmosphere on Earth sort of smears out the details of, in this case, this group of stars. As I said before, on this canvas, you will see things are not only white, in this case, these are very close by stars in our galaxy, but you will see things that are blue, which represent perhaps a larger group of stars, global clusters perhaps, or galaxies, for example. So let's move and take a look at what Hubble can do. 690 light years away, we're going to see something quite astonishing, in a region where they're surrounded by darkness, if you will. You're going to see appear a nebula, which is called a Helix Nebula, which is basically how our sun is going to die. And this is quite remarkable, in my opinion, because you see more detail coming in, but you really see this strange, colorful, beautiful image of this nebula. At the center of the nebula is a star that has ejected most of its outer layers, and is actually glowing on the surrounding gas that is actually lit up. And as we zoom in with Hubble, we can actually go and zoom very, very, very close to these little blobs here that I'm going to show you over and over again. And each of these little blobs contains like a mini solar system. These are where the stars are being born. And we can actually do this and see that the star at the center is blowing the gas away, and it exposes all these stars are being born in this region of gas and dust. By comparison, I forgot also to mention that you can actually do the same thing. You can ask, what is this? You can click on a pushpin, if you will, that we have developed, which tells you what you're looking at, what kind of category you're looking at, if you're looking at a planet or a nebula, and if you want to jump to a galaxy or perhaps something else, or to the actual data itself that's stored in our archives, you can actually go and fetch it from there. But the idea is, this is Hubble, this is from the ground. The resolution is quite incredible. And I'm going to show you how incredible it gets as we go even further away. So we're now 1,500 light years away from the sun. We're going to go and take a look at one of the best studies in nebulae. It's called a reflection nebula. There's stars embedded in dust and gas where they're being born, and they shine from inside. Before I show you that, why don't I show you this, which is, this image is taken from the ground. It's a famous nebula because it looks like a corset. And this is one telescope on the ground, this yellowish glow, and this is actually another telescope in southern Chile that's taking these remarkable images. And you're going to see many, many more colors coming from Hubble. But this is from the ground, low resolution. This is a little higher resolution from again, the ground. And then we're going to enter here an area that Hubble has observed. And I'm always astonished when I look at these images because you'll see they look like paintings to me. The yellowish washed out colors here are from the ground. That's all we can do from the ground. Hubble can instead take a look inside this nebula. So remember, the glow now comes from stars that are embedded in this nebula that are basically exciting the gas and shining through. And these colors represent the atoms that are being excited, whether it's nitrogen, whether it's oxygen, whether it's hydrogen. They excite at different colors. And these bands represent thick columns of gas that we'll see over and over again. And the colors are just astonishing. And again, as I said before, you can actually ask information about each of these objects. So this nebula has been studied so well that we made a three-dimensional model of it, and we can actually do a tour inside a nebula as if we had a very, very fast spacecraft. So as we enter the nebula, the colors are slightly different, but as you enter the nebula, you see many of those blobs that I mentioned to you before. You see the shocks of some bow shocks here. You see shocks here from stars being born and blowing gas away. And then if we had a magic wand, we could actually go inside one of these blobs and remove, if you will, its outer envelope. We can actually see prototypes of, this is obviously artist's rendition, but prototypes of what our solar system might have looked like maybe 4.5, 5 billion years ago when it was actually forming. So a star being born, blowing away its material, and then this ring of dust and particles actually eventually form our planets. Well, let's move a little further away. Let's go to about 2,000 light years away to another nebula. This is a nebula again. It's a nebula that has resulted by the death of the star, non-explosive death of a star like our sun, a small star, a relatively small star, slightly larger than our sun. And Hubble, you see this is from the ground again, you see the detail. I just want to show you this for the colors and the details. So you see, for example, there's, the colors are different. This is cooler, and this is much, the blue is much hotter. The red is much cooler, so we know the gas here is actually a little cooler than the gas that is being excited here. But again, these colors are quite amazing. Let's move a little further away to another nebula, 65,000 light years away. 6,500 light years away. We're not that far. As I showed you before, again, this is the ground, it's very coarse resolution. This is Hubble. Hubble shows you all these pillars. We call them pillars of creation because inside these pillars or behind these pillars we have stars that are being born and that shine. So you see stars that are being formed. You see the blobs that I showed you before. There are perhaps blobs are right there. There are a few blobs up here. I'm going to show you more in a second. This is 150 light years across. This was what generated and actually got astronomers started. This image here into understanding what these blobs were and that they were the seed of star formation, basically. These are called the pillars of creation. And you see each of these little columns, if you will, has inside many stars, some of which are being formed as we speak. And one of the other incredible things that we can do is, how would this look if I had X-ray eyes? Well, using Hubble, using what a telescope named Spitzer, we can actually ask that question because we superimpose images and if they're aligned properly, and ask ourselves how would images like this look at different wavelengths for people that for instruments that have different sets of eyes. And you'll see this in a second. So before we leave our galaxy forever, let's look at what I call the Hubble Nebula, which is an incredible painting, for lack of a better word. This is a nebula. This is gas. This is a star embedded in the nebula. And I just want to take a look, for you to take a look at the colors. There's a star at the center of this nebula, which is about 30 to 100 times larger than our sun, and it will collapse very explosively. And he's actually collapsing and sort of pulsating, and all these shocks here are from a single star inside this nebula. All these colors are gas being excited by the light, very hot light. This is the star right here. You see two blobs here. It's emitting a lot of gas. It's emitting a lot of its outer material, and it will explode. We've been waiting for it to explode for tens of years, but sometime it will explode. So you see power shocks here. And if I go back and take a look at how big this nebula is, this is a star right here. This is the size of the nebula, and this is 350 light years across. So Hubble in GoogleSky has the ability not only to look at things that are static, as I showed you at the beginning, but things that are moving. So this needs a little explanation. You see this image. Is it moving? Yes. Except there's nothing really moving. So let me explain this. We're 20,000 light years from the sun. This star is pulsating, is ejecting a lot of light, not any material. As the light goes through, clouds that look dark here, it lights the clouds, and this is what we see. This is the reflection of the gas that was already there. It's not moving, it's just being illuminated by the central star. And Hubble has observed this at least 4 or 5 times, and we actually were able to make an animation of what the expansion of the light coming from the central star, how the expansion acts on the surrounding environment. Okay, one last thing before we leave our galaxy. I forgot. Let's go 25,000 light years away. Let's go to the center of our galaxy, just to give you an idea that we have very, very many stars at the center of our galaxy. The center of our galaxy is a very crowded place. There are billions of stars. This is from the ground. We cannot even identify anything. And this is the image that Hubble is taking. And every single dot here is a star. This is a very, very tiny field of view that Hubble has. And every single dot is a star. The red ones are cool, the white ones, the blue ones are very, very warm. Okay, we're ready to leave our galaxy, and the number will grow. We're 160,000 light years away. We're going to take a look at the Large Magellanic Cloud, which is our sister and galaxy fuel, one of the two. This is a irregular galaxy. It's not shaped like a spiral galaxy. It is being torn apart by the gravitational pull of our own galaxy. And it's full of stars. It's a clump of stars. And these stars, as you see from the ground, Hubble has revealed a very interesting clump of stars. There are about 1 million stars here, all clumped together. And again, this yellowish goo, I don't know how to call it, it's brown. This is what Hubble can distinguish individual stars at the distance of other galaxies, about 160,000 light years away. In this particular galaxy, there are lots of stars that are forming, a lot of stars are exploding, and Hubble actually found a little treasure, which is, we found that if we look closely, we can actually find the remnants of a star that exploded over 1,000 years ago in this particular galaxy, which is near to our own. And then you can see how the resolution from Hubble can improve the information. This is actually not great, but it's pretty good. You have to understand that every dot you see here, no matter how squashed it is actually a star. Now let's take a look at galaxies as big as our own. Everything you see here, by the way, there are stars. I'm going to show you how small this patch of the sky is that's been observed by Hubble, because we're going to compare this with a very large galaxy, the Andromeda Galaxy, which is the other galaxy, the twin galaxy, if you will, to our own, in what's called the local group of galaxies near our inner nebula. This is what Hubble observed, all the galaxies that you saw, and this is a very big galaxy. Andromeda is a galaxy, again, as I said, like our own. It has two companion galaxies, very similar to the ones we have. Perhaps this is actually more similar to the Large Magellanic Cloud that I showed you. And as we did before in GoogleSky, we can ask information about this galaxy, what type of galaxy it is, how far it is, and then we can have information about not only its location, but where the data for this galaxy was observed and how you can get it. Now, one of the exercises we can do is we can ask, what if we had ultraviolet light eyes? And we can actually look at the very, very hot stars in these galaxies that emit in the ultraviolet. Well, this image right here, superimposed on the Andromeda galaxy, is actually an image from the galaxy survey. And you can see that there's a quite a remarkable difference between the image in the optical, which is what you and I or Hubble would look at, and the image in the ultraviolet. This is actually very powerful for astronomers because different types of wavelength, different types of colors tells us something different about the underlying population of stars, in this case, that are present in Andromeda. We're going to go now even further away, millions of years away. We're 11 million years away. We're still pretty much in our neighborhood. But we're going to take a look at an object that Hubble has observed, the center of the galaxy, that contains a black hole, which is 1,000,000 times larger than our sun. There's a black hole at the center of this galaxy. And this galaxy doesn't seem that strange to some extent. There's a lot of gas here. There's been funnel at the center. But to some extent, it doesn't seem that strange as viewed from Hubble. Except when you turn on your X-ray eyes, you can see that this seemingly ordinary galaxy has a big secret. This is the gas that is being ejected from this galaxy and is being funneled at the center. And this gas is very hot, it's millions of degrees. And this is actually the size of the galaxy. And with Hubble, we only see very little just because we look at it in the optical, in the optical only. But with X-rays, we actually take a look at gases millions of degrees warm. What about the Sombrero galaxy? This is a beautiful galaxy that my colleague Christian observed for what's called the Hubble Heritage Program. And we're looking at the galaxy edge on. And you see why it's called the Sombrero. And it's a very nice galaxy, just a few tens of, maybe 30 million years from probably light years from our sun. It's called Sombrero because it's covering some of the sombrero, but I just want to show you the detail that Hubble can see here. The other galaxies that look very, very different in different wavelengths. So this is, again, an ultraviolet image of a galaxy that Hubble has observed. We're going to remove that. I'm going to show you, this is from the ground. The edge here is Hubble. I'm going to show you what kind of detail we can see in this galaxy. There are two galaxies here. One is ripping the other apart. This is the big one. It's ripping this one apart. And these blobs here, this blue and red blobs represent places where stars are being formed. This is the tail. This is the tail that is disrupting this particular galaxy. And you see disruption and the details of it you can see. But I found astonishing how well Hubble can actually see something that our eyes didn't really look for at the beginning. You can see even galaxies that are much, much farther away than the galaxy we're looking at, way, way in the background, that are forming other stars in these little blobs here, very big stars, and are probably merging like this one is. We can even move further and take a look at things that are not just in environments where galaxies like our own, where there are just a few galaxies, but where there are lots of galaxies. Now, you're going to see now, this is called Messier 87. It's a very, very big galaxy. All these blue dots are members of this cluster. They're all galaxies. Each of these dots, blue dots, is a galaxy smaller than our own, but still a galaxy with probably hundreds of billions of stars. Hubble has the ability to observe this, and I'll show you what it does at the center, but we also can put our X-ray eyes here and see how much bigger really this galaxy really is. There's a very different picture here. There's probably the biggest black hole we ever found, perhaps tens of millions of solar masses inside here, inside this particular here. And you see gas being funneled at the center of the galaxy. This galaxy is hundreds, if not millions of times larger than our own galaxy. And at the center, Hubble has discovered something very remarkable. The black hole at the center of the galaxy is emitting a jet several hundreds of light years across. And the jet is being emitted like a jet because it's trying to find a lot of gas in here, and it can't sort of absorb it all. So one of the mechanisms is actually to get rid of it. So you see galaxies here, perhaps these two galaxies right here, these two little dots are probably as large as our own. And in this cluster, all these blue dots actually belong to this particular large cluster of galaxies. This is another particularly large galaxy, an elliptical galaxy in the cluster, which is called Virgo cluster. In these environments where galaxies are smashing together, where there are many, many galaxies, interesting things happen. And this is one of my first love when I started being interested in astronomy. I like things that smash together. These antenna galaxies, two galaxies that are smashing together, they've been smashing for a few million years. And you see these tails, they're called the antennae because they have these two antennae here. They're called tidal tails. These are basically the center of two galaxies that have been smashed together. They're passing over each other. And you see, the blue, remember, is very hot. Lots of stars are being formed. The red is a little older. So you see these older stars, and the stars sort of smashing and forming here, clouds, and then you see a lot of dust, where many, many, many more other stars will be formed. In these environments, there are actually something that Hubble is observing in detail. This is called the mice. Again, two galaxies, and you see why they're called the mice. They look like two mice running after each other. When I rotate, this is a tidal tail again. All this is very blue, so by now you should know that there are a lot of stars being formed in here. And there are two galaxies that are, again, passing by each other, ripping each other apart. This is the center of one being ripped apart, and this is the center of the other. What's remarkable is the detail with which I see other galaxies. That's a galaxy in the background. That's a galaxy in the background. That's another galaxy in the background. That's another galaxy in the background. So Hubble not only gives us an image of galaxies merging, and the other ones, one mouse and the other mouse. But we also have very interesting information, which is very useful to us, to know, even if we're not just counting how many galaxies we have in the universe, we have information again about our local universe and how galaxies merge. Another very interesting one, which is actually I saw in my office, because I really love this galaxy, is called the tadpole. Galaxies in a different phase of merging. These are much, much closer together. They merged. There was a nucleus that went by. And this very long tidal tail where, again, lots of stars are being formed. These are hundreds of millions of stars being formed here. And then all these dots, all these elongated things are just galaxies that are far away. And this is really incredible because this is how Hubble actually resolves and takes a look at galaxies that are far away. So every single dot in here you see it's a galaxy. If you go to even denser environments, we experience something that's called gravitational lenses. So we have a galaxy behind a very massive cluster of galaxies, and we look at this from the point of view of Earth, and we see very strange things happening. We see very strange arches, and very strange arcs, here, which are basically the image of a galaxy that was behind the cluster being stretched by a lens, except the lens is actually the gravity of this particular cluster. And so this was a very big success of Einstein and general relativity because this was predicted that mass curve space, then light should be curved, and then this is quite a remarkable example. And Hubble has observed many of these. One of these is Isabel 1689. Again, all the dots in here you see, except for very few, are galaxies. These are galaxies much, much larger than our own galaxy, but all the dots are galaxies. These galaxies are likely to be the size of our own. But then you see these filaments here, which are the image of galaxies behind this cluster that are being stretched by the gravitational pull of this gigantic amount of mass concentrated in this region. So before I show you the last image of Hubble, I thought I'd let someone, which is better than me, which is a group at the Space Telescope Science Institute that does press releases, show you what we witnessed so far and why Hubble has been so impressive.
Galaxies are like islands in the sea of space. They glow with the light of billions of suns. The Hubble telescope reveals nearby galaxies in exquisite detail. Galaxies like these fill the universe. We see an astonishing array of distant galaxies. once were. In one tiny region of the sky, Hubble finds some 30,000 galaxies. Within a single image, we can explore 10 billion years of cosmic history. Relatively nearby galaxies are fully formed, with complete spiral structures and smooth elliptical shapes. As we travel farther into space, we see galaxies as they were further back in time. These galaxies appear somewhat disheveled, with their mature structures still developing. When the universe was young, newly formed galactic disks were ablaze with star formation. Beyond this point, clumps of stars that are beginning to form galaxies. We've seen but a handful of the billions of galaxies stretched across space and time. Just one small sliver of the universe, observed by Hubble.
So I thought this was very interesting. We're going to look at this again for a second, because when I was studying this particular image, this is the deepest image ever taken by Hubble, and I think by mankind, of the universe. This is a patch of sky that was selected because we couldn't see anything else but any other telescope, and we observed this, and we find tens of thousands of galaxies. So every single dot in here is a galaxy. I remember when I was a graduate student, when this image was released, that the first thing I did was count, given the size of this patch in the sky, how many galaxies do we have in the universe? And just to give you an idea, the size of this patch of sky, where you see many, many galaxies, is a penny, is as big as a penny if you hold it in your arm's length. That's how big it is, or how small it is. But the incredible things, as the video just showed, that you see pieces of galaxies that are coming together billions of years away. Only some of them are just a fraction out of the age of our universe. And then it's a picture that is so different than what we see nearby. The galaxies are very fully formed. These are probably local galaxies that are closer to us. But to me, the remarkable thing is that every single dot in here is a galaxy. And if you calculate how many we have in the universe, that makes you feel a little small, because it's probably over the order of 200 billion. And each of them has hundreds of billions of stars in it. And I'm going to end here, but I just want to reiterate how incredible this is. I don't know if you can see it here, but for example, this galaxy is probably two merging galaxies with little dust across here. These are actually forming. This maybe is merging. This blue here, so maybe it's something else forming. So I will end it here. We're going to take some of your questions. Your questions in the section. That's my website. If you want to send me an email or call me up, or call me up on my phone. No one answered, but call me. If you have any questions, and then once again, my collaborators are Dr. Christian, Josh is here. He will be happy to answer questions, and I'll take your questions. Thank you very much.
We do have time for questions. Since it's a little hard to hear in this auditorium, when you're asking a question, if you would please stand and try to speak up.
The Hubble also takes spectral data so that you can actually figure out the motion. And the question is there a place on the site where you can actually see motion of galaxies? So that's one question. And then another quick question is, how quickly are the Andromeda and our galaxy approaching? You're fine.
Okay, so the first question is, so it's true, I didn't show you this. So Hubble can take, so if you recall, for example, in the last video I showed, you see that we do this 3D thing. where we actually fly. Okay, the way we do this is we can compute distances to galaxies. We can take their spectrum and figure out how far away they are from us, and then we construct a three-dimensional environment. And actually, I have to tell you, that video is nice, but if we had to play it at the scale of the universe, it would have taken several days for me to go from one galaxy to another. That's how far they are. So we had really to crunch it all together. So yes, we can measure the distances to galaxies. Now, measuring motion of galaxies, right now it's not possible. Sorry, it's possible, but we're not able enough to distinguish again the motion because they're too far away. So we can measure stars and how they move in their own galaxy pretty reliably up to some distance. But then the motion becomes so small because Andromeda is 2.5 million years away. The resolution that you need to measure are pixels that we haven't invented yet. We can't do that. We cannot do that. If we could do that, then we can actually calculate a lot of interesting things. We do have other measurements for Andromeda, to the second question, to figure out how long it's going to take. It's going to take like 1 billion years, so you're fine. And there are people actually have taken this a little further. They actually put themselves at the center of the Earth, and they actually look at the sky and saw what happens when Andromeda comes by and rips the entire solar system apart. It's a very interesting thing. But they will merge in a very typical manner, like I showed you, like all these galaxies, like the mice or like the tadpole. They're going to basically come together. We know actually how they're going to come together, predicted from the distances and the velocities that we see in some of the stars in Andromeda. And we know that they're going to come together maybe 1 billion years, and eventually they will all merge together in one big fat round galaxy. But we won't be around to see it, unfortunately.
Yeah. What is the availability of GoogleSky, and how many satellites on that picture way back when around the Earth are there?
I can't remember the number. Okay, so if you have Google Earth, you have GoogleSky. So it's built inside. So I should actually show you. Well, I don't have to. But so in Google Earth, there's a menu bar at the top. That's a sign of a little planet. If you click on that planet, there's a menu that drops down and says Sky, Moon, and Mars. And it will switch the point of view. So if you say Sky, it will switch basically and show you exactly what I showed you. And as for the satellites, I don't know, 30,000 maybe. I don't know. We wrote this code that actually goes to, there's a site called Space Track that tracks all this. Yeah, to NORAD, yeah. So we go to NORAD. NORAD tracks everything bigger than 3 centimeters. So actually there's much more than I had here. Here I know things are bigger than a couple of meters or so. And it tracks all the debris because that's what actually you need to know. And I think, don't quote me, I think it's 30,000. I can actually figure it out. Maybe 30,000 is a little high. Maybe 30,000 is global. It's debris and satellites. There are a lot of debris. So for example, the first thing we did, Josh and I, was when we plotted the debris, we went to look at, the Chinese decided it was a good idea to blow up the satellites in space. So you can see a trail of debris all over. Very, very dangerous for many satellites.
The debris we populated on the sky was everything over 1 meter, basically. So that was the stuff in red. The satellites was blue, obviously.
So it's a large number. And many of them are dead. I mean, they work for a few years and then they die. So. Sorry, I had him and then I was missed.
Yes. I found this slide one of the most interesting places in the solar system. That is the Pluto-Charon system. It's interesting because the center of gravity of that system is outside the surface of Pluto. So that seems to be a gravity well that you could probably use for propelling something. I don't know how well you could use it. But my question is more trivial than that.
Good.
You showed a cross-shaped star. I never understood why we get those.
Well, because I don't have an image here, but I can actually show you. So here. Let me see if I can. Is it over here? Yes. In order to hold, so the way the Hubble telescope works is that there's a very large, there's a mirror about 2.5 meters across on Hubble, the mirror where the light comes from. So I'm the mirror, the light comes from the star. But then this light has to be focused someplace. Okay? And so the light is focused basically on a secondary mirror, which is in front of me. And then I would have a hole in here where the light will go through again to the instruments behind me. Unfortunately, I don't have an image to show you, but let's see if you understand this. But So what happens is there's a support structure that holds the mirror, the secondary mirror, which gives rise to this crosses. All telescopes have them. Those crosses show only if the object is small enough to, like a star, for example. So if the object is basically point-like. So at these distances, Pluto is almost point-like. And so we have the reflection of the structure basically onto the image. So that's how it's very easy to recognize stars from. Let's see if I can show you stars from. I cannot show you here, but a little harder to do. It's very easy to recognize actually stars from galaxies in. Unfortunately, I cannot show you here, but it's very easy to recognize stars from galaxies in. I'm trying to find if I can go back here. Stars from galaxies in images, because all the stars, since they're like at the distance of our telescope, they're basically a point. They don't have any dimensions, if you will. They do, but it's so distant that is irrelevant. And so they produce what's called a diffraction pattern, which is this thing, this sort of cross that you see up here. And this cross actually shows up in all the images of stars that you will ever see in Hubble. If it's an extended object, the light is diffused, and we don't see this, and that's why galaxies we don't see that.
Well, I've seen those on the moon, from the moon too, just with the naked eye. Why do I see, and why are they upright?
I don't know. Let's think about it. Really? I don't know.
I was wondering if you could talk a little bit about the Lunar Orbiter Image Recovery Project and how that newly digitized archival data might fit into this.
Yeah, so it's not my field, but I'm glad to tell you. So there's no, in a sense that I'm not a library scientist, but I mean, so the images that we have of, there have been a lot of images that have been taken about from the moon, and so what I showed you, the best thing would be actually to show you here on Earth. But that's the blue is not working, but blue is. Well, this loads, I can actually show you. So, there's lots of missions that have been trying to map the moon to, let's say, meter or so resolution for some time. There was a mission called Clementine that actually did very well over the past few years, and whose main mission was to, we don't have internet here. Never mind, you're going to have to do it at home. Sorry. So the idea is that the Clementine mission, for example, which is one of the precursors for this mission, was tasked with trying to find the presence of water at the south pole of the moon. So even though we have visited the moon several times, we really don't have very good maps of the moon. Actually, if I had internet, I could actually show you. We have very, very good maps of Mars, and we don't have that great. We have some information about the moon, but it's not as great as you think. And you would think, being a satellite, that it'd be observable. So we can observe it. Unfortunately, for reasons that are technical that I can discuss if you're interested, we cannot observe the moon directly with Hubble, other than with it's very difficult. It's so close. Pointing telescope is very, very complex. So we cannot do that. Otherwise, Hubble would be very, very good at observing. But the idea is that basically we want to map the moon to meter or sub-meter resolution. All over like we do on Mars. There's a satellite on Mars that is doing this daily. Actually, if you go on Google, if you go on Google Mars, inside Google Earth, you can actually see where the Mars Reconnaissance Orbiter is observing, basically. You're going to be able to do the same thing if Google puts the feed up for the moon.
Quick question. During your speech, you had said that you were measuring the light years from Earth, and then later on you said from the Sun, and I was wondering which one it was, or if there was a change in how that noticed.
Okay, so when you get to millions of light years away, the difference doesn't matter. The difference is only 8 minutes. So the light from the sun takes 8 minutes to reach Earth. So I guess I'm an astronomer, so I'm Earth-based, but when we go to distances of millions of light years, 8 minutes don't make a huge difference. But you can measure it, from Technically, what we see here is measured from Earth because that's where we measure it from. But the difference is only 8 minutes. So 8 minutes at 2.5 million years, it's not relevant to some extent. So it doesn't really matter. So what, if you go to like I showed you, if you go to Jupiter, for example, when it's hours, maybe minutes matter. I would argue not there, but technically everything I showed you was from Earth, from the solar system, if you will, when you get to very large distances.
Is there one last question?
I know you guys are counting on the James West telescope, but I understand Congress has canceled it. And where is that going to leave you?
Well, so we are counting on James Webb Space Telescope. Congress has tried to cancel it. So the House representative has zeroed out the budget. The Senate has reintroduced the budget. And next Tuesday we'll discuss what to do with it. So the discussion is, I don't want to get into political discussion here, but so the discussion is open right now. So the James Webb, if you thought that what I showed you with Hubble was interesting, James Webb has 6.5 times the area of Hubble in terms of collecting area. It will take us to see those tiny little galaxies for which I just showed you the pieces that Hubble was able to see. And it will do that in a fraction of the time that Hubble can do. So it's truly going to be a revolutionary instrument. But it's expensive because not only is it larger, but because we have to build technology that didn't exist when we build the detectors and the mirrors. The mirrors are built of beryllium, which is a pretty expensive metal, and they have to be kept very, very cold at 40 degrees above absolute zero. So what happens if they cancel it? So if they don't cancel it, we are much happier because we think, like Hubble revolutionized optical astronomy, I think James Webb will revolutionize infrared astronomy. And by infrared, I mean the early universe, that's what we want to look at. If we don't, if the Senate and the Congress decides that they don't want to fund NASA to build James Webb, then we are in a little trouble in the sense that astronomy does not have anything else in line to cover the James Webb Telescope if that's canceled. So meaning that we will have to wait maybe 15 years for something else to be put to it, in the drawing board. And there are other missions. We proposed missions even larger than James Webb, but it's hard. I think we have to go one step at a time. I'm optimistic that they might actually change their mind. It turns out that the increase in budget that is needed to fund James Webb is about 1% of NASA budget. So, which is about $200 million a year over the next 5 years. That's what needed. That is not being allocated. That's what the arguments are about. There are some indication that they might come to a compromise. As I was talking to Josh before, is the compromise cannot be we're going to give you half of what you need because then you can fly. So it's either they fund it or they don't fund it. And so we're really looking forward. And so I was actually speaking with Dr. Mikulski 2 days ago, and they're going to discuss it next Tuesday. So you'll read it in the papers.
Want to add something, Josh?
Yeah. The last question you had, I just wanted to throw in some numbers about, light, and Alberto was talking mainly in, light years. So just to give you some comparative numbers, we measure the distance from the Earth to the Sun in astronomical units. 1 AU is 150 million kilometers, okay? So 1 light year is about 10 trillion kilometers. So just to give you a number that's a little more easy understandable, okay? So hope that clears it up a little bit.
Yeah, sorry, I think there was one here.
Yes, I think there's one last question, right? Did you have a question? Yeah.
Yeah, what's the API look like for this, if there is?
It's actually pretty cool. It's actually very well, API for people that don't know, it's an application program interface, so how you actually can put your own things up here, you can write your own code. It's actually, it's well developed because the GIS community, the Geographic Information System, it's called KML, Keyhole Markup Language. Keyhole was a company that bought
So it works on Sky also?
Yes. There's a tag you have to append to the header of your file to tell it I'm in Sky, so it knows to ask you to switch the camera, so to speak. It does automatically. But then once you're done, it works almost the same. There's some issues with altitude. There's no altitude in the two-dimensional sphere that the sky is. But other than that,
One more time.
Well, there was this lady there that's been.
All right, there we go. Two more, here we go.
I'm not sure if they're about Google, but I was wondering, can you put any price tags on what you did to give this to us?
Oh, I'm paid by NASA, so it's all free. That's my job, and we did at the beginning. I wrote a proposal to Google in 2006, early 2006, and then I remember working nights and weekends because my bosses where I worked didn't think that this was going to work. And then it was funded internally, and we could do work, but it's all stuff that we do. It's all work that we do for the general public, and I'm a very strong believer. I was saying this at dinner that one of the things we should do, one of the things we should do, that's my computer taking over. One of the things we should do is really communicate science, and this is a very nice tool to communicate science because it puts. There's no difference between you and me. You can do exactly what I showed you tonight. I just took videos because it was easier, but I could have done a demo, live demo, for an hour. You can do exactly the same thing. You can browse Sky, you can see the Hubble, you can have images. You can go download the data. So the price tag is zero. And to be honest, we didn't just do Google Sky. We also partnered with other industry like Microsoft. There's a competing product, very similar, and in some ways a little bit better in some areas, called the Worldwide Telescope. That can run on Windows in this case. Google Sky runs on anything pretty much. That has made different choices on how you visualize, but the idea is the same. We want to expand, we want to allow anyone to look at the solar system, at galaxies, at telescopes, at space in a very, very different way. This is much more immersive. I mean, when I was a kid, I was dreaming about something like this, and today I can actually do it on my iPhone. Almost.
It seems like some of the amounts of money you're talking about are small enough that if Congress won't fund them, you could appeal to the general public or to rich people to fund some. One of them is back here, Mr. Gates' companion.
Yes. Simone, Charles Simone.
One of them.
Alex. Oh yeah. So actually, the Space Telescope Science Institute is funded by NASA to operate Hubble. We're a non-profit. We cannot raise funds at all. So everything we do is funded. It's my own time, so we cannot raise funds. So that is not going to work. I tried many, many times, but they won't change. But, we try with Josh very hard. So it's a non-profit. If someone comes along and decides to do so, Paul Allen has funded it. Well, had funded because now the funding has actually been cut pretty drastically. Bill Gates donated $10 million to an effort to build the largest telescope in southern Chile. Charles Simone, which was the guy who invented, or actually wrote Excel, donated $20 million for the same effort. So there are some donors, but the problem is that doing science is actually expensive. So 30 million is almost like a drop in the bucket when the cost of the entire instrument is 300 or 400 million or $500 million. So, the James Webb will cost $8 billion. And Hubble was maybe $4 billion when it was built. So, unfortunately, to do this type of science, I don't know, if you know someone that has billions, please call me, because that would be useful, and if you can donate, or maybe start your own company or volunteer. I think it's still going to be hard, and you're right, the amount of money they're considerable, because I don't want to trivialize this. $8 billion is a large amount of money. But I have to say, and I always say this when I give these talks, and I don't think I'm going to be wrong, is that Hubble is the second most successful telescope of all time after Galileo's telescope. I mean, we have really changed astronomy. What I studied, when I studied astronomy 20 years ago, I didn't know anything. I didn't know all the discoveries that Hubble was going to make, and I couldn't even imagine some of them that were made. And we were just blown away by all the discovery that was made. And the James Webb has the capability to answer questions we don't even know how to ask right now. And so I don't know how to put a price tag on that. How do you put a price on discovery? Right? That's very hard. That's why it's very hard to sell. I mean, pretty images help, but then there are costs. So.
Thank you very much.
Thank you.